Space is three-dimensional, so why doesn't our solar system look three-dimensional? Why don't planets orbit the sun from every direction, above it, below it, sideways, and diagonally, like a swarm of bees circling a glowing hive? Instead, something strange happens. Mercury, Venus, Earth, Mars, Jupiter, and Saturn all move around the sun on nearly the same invisible sheet. Different distances, different speeds, but almost the same flat plane. From far above, the solar system looks wide and circular, but from the side it looks surprisingly thin, almost like a vast cosmic pancake. The sun sits near the center, and the planets trace graceful paths around it. But why? Why this beautiful, almost unnerving flatness? The answer takes us back billions of years, long before the sun ignited and before Earth was even a whisper of dust. It begins with a truly enormous cloud, a colossal, cold and dark nebula of gas and dust drifting silently through space. Within this primordial mist lay all the raw ingredients to build our star and its family of planets. But to begin, the cloud needed a little push, a gentle nudge to start it turning. This initial rotation was likely very, very slow, almost imperceptible. It could have been sparked by the shockwave from a nearby exploding star, or perhaps by the subtle gravitational pull of other passing stars and cosmic matter. Whatever the cause, this slight initial spin was the crucial first step. It set in motion a chain of events governed by fundamental physics. The cloud began to contract under its own gravity, pulling gas and dust inward toward a common center. It was the beginning of a magnificent cosmic collapse, a process that would ultimately give birth to our sun. As the immense cloud began to shrink, something magical happened. The slow, lazy turn began to accelerate, getting faster and faster as the cloud grew smaller and denser. You can see this principle on Earth. Think of an ice skater pulling in their arms. The journey from a formless 3D cloud to a flat 2D disk was underway. It's a tale of gravity, spin, countless tiny collisions, all working together over millions of years to sculpt the familiar, pancake-like home we inhabit. The cosmos, it turns out, is a master sculptor. Imagine you're inside that spinning, turbulent cloud. Particles of dust and gas are flying everywhere. Some are moving up, some are moving down, others are orbiting nicely around the middle. It's a chaotic cosmic traffic jam. When two particles on wildly different paths collide, something has to give. Their vertical motions tend to cancel each other out. It's like two people running into each other head-on. They both stop. The energy of that up and down motion is converted into heat and lost. But the one direction they mostly shared was the cloud's overall spin. When two particles orbiting the same way collided, they didn't cancel their sideways motion. They tended to merge or settle into a similar, averaged-out orbit. Over millions upon millions of years, this had a profound effect. Countless collisions dampened erratic up and down motions and in and out motions. The high-energy random motions were averaged away, leaving only low-energy motion. And what was that most stable motion? A circular path in a single, flat plane, all moving in the same direction as the original spin. Particles that strayed too far above or below were more likely to be knocked back into the crowded mid-plane. The system settled into its lowest energy state, a thin, rotating disk. Chaos turned into order through simple collisions. The cosmic pancake began to take shape on the stellar griddle. This flattening is universal. We see it everywhere in the cosmos. The rings of Saturn are a perfect miniature example, incredibly wide yet astonishingly thin, because countless icy particles have collided over aeons, cancelling their inclinations, settling into a single plane. The same principle shapes spiral galaxies like the Milky Way. Conservation of angular momentum and internal averaging. Once the protoplanetary disk was formed, the stage was set for the next act, the birth of the planets. Within this flat, rotating sheet of gas and dust, tiny grains began to stick together. Electrostatic forces, like static cling, caused the first dust bunnies to form. As these clumps grew larger, their own gravity started to pull in more material. They grew pebbles, boulders, planetesimals, small, primordial planet bodies. Eventually, after tens of millions of years of sweeping up material in their path, they became the planets we know today. Because all of this material was already orbiting in the same flat plane and moving in the same direction, the planets naturally inherited these characteristics. It's why, in a model of the solar system, all the planets' orbits lie on what we call the ecliptic plane. They are all coplanar. Furthermore, they all orbit the Sun in the same direction, counterclockwise, seen from above the Sun's north pole. This shared motion is a powerful piece of fossil evidence, a direct fingerprint of the spinning disk from which they were born. This orbital harmony extends to the planet's own spins as well. Most, including Earth, rotate counterclockwise. It's as if the entire system retains a memory of that initial gentle spin of the primordial cloud. Of course, there are fascinating exceptions hinting at a more violent past, but the overwhelming pattern is order and consistency. Gravity, primarily the Sun, and the significant influence of Jupiter, acts as the great shepherd, keeping planets in predictable, nearly circular paths. Tiny nudges can make orbits wobble over vast timescales, yet the system's fundamental flatness endures. While the cosmic pancake explains the main architecture of our solar system, the story includes exceptions. These outliers are fascinating. They reveal more violent chapters in our history. Many comets follow highly tilted, extremely elliptical orbits, swooping in toward the Sun from high above or far below, the ecliptic plane. They likely originate in the Oort cloud, not a disk, but a vast spherical shell of icy bodies that surrounds the solar system. So far from the Sun, these objects were never fully incorporated into the flattening disk. Their orbits weren't averaged by collisions. Occasionally, one is nudged inward to pay us a visit. Even closer in, beyond Neptune, many Kuiper Belt objects are noticeably tilted, suggesting a turbulent, stirred-up past. Gravitational interactions, especially with giant planets like Neptune, likely flung some bodies into more inclined, eccentric paths. And Uranus, it spins on its side, probably knocked over by a colossal impact early on. These exceptions don't disprove the pancake, they enrich it. In the end, our solar system is flat because it was born from a spinning cloud. Conservation of angular momentum, and countless collisions, forced it into a thin, rotating disk. The planets formed within that disk and inherited its orderly motion. This process isn't unique. Telescopes reveal similar disks around young stars across the galaxy. As you look up, picture that colossal, slowly turning cloud collapsing, spinning faster, flattening into a brilliant disk where planets emerge and trace their graceful paths.